welcome to Math with Master. Today we are going to learn work power energy part 1 work. So this is a very important topic in JEE advanced physics. So let's go. So basically what is work? When a force is applied on a body and point of application of force displaces such that there is a finite component of force in the direction of displacement, then it is said that the work is done by the force. Quantitatively, the work done is the dot product of force and displacement. So we can write for work, let's say some small work dW is equals to F bar dot dr bar. Here the dr bar is the displacement, the small displacement, and F bar is the force. So if we integrate on both sides, the work done will become integration of F bar dot dr bar. So let's say if our force F bar is constant in both direction and magnitude, then we can write dW is equals to F bar dot dr bar, which we can write delta W is equals to F bar integration of F bar dot dr bar, which is equals to F bar dot integration of dr bar. Since F bar is constant, we can take it outside of the integral. So delta W is equals to F bar. The integral goes over, let's say, R1 bar to R2 bar. So we can write F bar dot R2 bar minus R1 bar, which is nothing but the net displacement F bar dot dr bar. So we can write this if the force is constant. And also we know that if we write something in dot product, let's say this example, delta W is equals to F bar dot delta R bar. So we know that we will write the magnitude of F bar, the magnitude of delta R, and cos theta, where theta is the angle between F bar and delta R bar. So delta R bar is nothing but displacement. Let us say that the delta R bar is something like this and F bar is like this. Now if you draw a component of delta R bar, let's say the angle between them is theta. So the component of delta R bar on the force direction, in the direction of force vector, will be delta R into cos theta. So this we can write as delta W is equals to F into delta R cos theta. So what we can write is the work done is also equal to force into component of displacement along force, means in the direction of force vector. Okay. So now let's say an example. A body of finite mass is lifted vertically upwards to a distance S by a constant force F against gravitational force. Find the work done by both forces. Here both forces means the gravitational force and the force which we are putting the constant force F. So now there is a body. In the first case, it's being lifted up by a distance S with a constant force F. So you can see the direction of displacement and force are same. So we can write that delta W is equals to F bar dot S bar. Since here the force is constant and displacement is S bar, we can write F into S into cos 0 degree, because they are in the same direction, so there is no angle between force and displacement. So this is nothing but F into S. The delta W is F into S. And gravity is acting in the downward direction, and the force of gravity is mg. So here the angle between mg and the displacement vector is 180 degrees. So the work done by the gravitational force will be force due to gravity dot s bar. So this will be force due to gravity mg into s into cos of 180 degrees. So the gravity has done a negative work of mgs. So let's take the second example. A person holding a block of mass m moves horizontal through a distance, let's say s. Then find the work done by gravitational force. So this is a simple case. While the gravitational force F is equals to mg is acting downwards and the body is displaced horizontally, so the angle between them is 90 degrees. So what we can write is delta W is F dot S, which is equals to mg, the magnitude of F, into S into cos of angle between them is 90 degrees. Since cos of 90 degrees is 0, the work done by gravity in this case would be 0. And let me also tell you that if angle between, here theta is angle between F and S, if theta is less than 90 degrees, then the work will be positive, since cos theta is positive when the theta is less than 90 degree. If theta is equals to 90 degree, then the work done is equals to 0. And if theta is greater than 90 degree, then the work done will be negative, since cos theta is negative between 180 degrees and 90 degrees. So this is what we have to know, the basic information. Here theta is the angle between F and S vectors. Okay. So now let's go move to this example. In this example there is a simple pendulum which is acted upon a constant horizontal force F, and the question asks us find the work done by the force F, find the work done by the gravity, find the work done by the tension. So now let's draw this pendulum. Here the force is acting in let me mention you, this is a constant force and its direction and magnitude both are not changing. So let's say it went up to an angle theta and it came in its equilibrium position. So the force will be something like this. Let the length of the pendulum be something L. So this is theta. So here you got a triangle like this and some extra length over here. So since this is theta and this is L, we can write this length as L into sine theta, this as L into cos theta, and we know that this total length is L. So we can write this small length as L minus L cos theta. Okay. So what is the work, let's say the first case, work done by the force F is equals to, since the force is constant, we can write F into the net displacement. As the force is in horizontal direction, we can also write the force into displacement in the direction of force, the component of displacement in the direction of force. I have told you in the earlier example, sorry, not the earlier example, in the concept. So since the force is horizontal, F into the component of displacement in the direction of force means component of displacement in the direction of horizontal direction. So the horizontal displacement is just L sin theta, as you can see over here. It's just L sin theta. So we can write F into L sin theta. So that's all. F L into sin theta is the total work done by the constant force F. Now we will go to the second part of this question. He is asking find the work done by the gravity. So we can write delta W by gravity. Gravity here is also a constant force. It's always directed vertically downwards towards the earth. So we can also write F bar dot S bar directly, which is equals to the magnitude of gravitational force is mg into the displacement in the direction of, so here we can write component of displacement. So I think you remember the formula, magnitude of force into component of displacement in the direction of force is also called as work. We can find out like that also. So we can write mg into component of displacement along force. So since it's vertically, the component, the gravitational force is vertically downwards and the displacement here is vertically upwards in vertical direction. So there should be a negative sign, mg into the displacement is L minus L cos theta. So this is, as you can see here, so this is the work done by the gravity. So let's move to the third part. What is the work done by the tension? This is the most interesting part. So for at any instant you take this pendulum at any instant, let's say at this position, it is at some angular position theta and it's going somewhat upper more. So what you can see here, let's say this is a very small angle d theta. So the displacement is like this. Let me change the color. So here the green color one is the displacement. Okay, it's a small displacement when the angle has changed in d theta, and we know that tension acts always like this. So this is dr, the small displacement, and this is t bar. We are not writing directly F bar into S bar should not be written for tension, because here tension is not a constant force. It's not constant force because even it's changing its magnitude as well as it's changing its direction. So we have to use integration of T bar into dr bar. Here T is nothing but tension, but as it's a force we are writing T instead of F. So it's the delta W. So you can see we can write this as integral of T into dr into cos of angle between them. And if you look closely, for a small change this angle is nearly 90 degrees. So we can write this as cos 90 degrees, which will eventually become 0. So the work by the tension in this case is 0 because tension is always perpendicular to small displacements. Okay, so let's go to this problem. This problem is slightly more complicated than the other examples we have discussed before. So let me explain you what this question is. So the block is resting on the ground we have tied it with a string and we have passed the string over the pulley and we are applying a constant force F. So theta is the angle between the string and the vertical from the pulley. So we have to find the work done by the constant force F when the body moves from the position theta 1 to theta 2, assuming that the y remains constant during the process, which means that body is not going in air suddenly. It's a normal process. So there's a ground like this. I have to draw somewhat bigger. So let's say this is the position theta 1. There's a constant force F, and after some time this comes to a position theta 2 like this. Okay, I hope you understand. This is the vertical, and here the angle I am highlighting with this color is theta 1, and it has gone to theta 2. This is theta 2. So for solving such type of questions, now here in this question, the force is continuously changing its direction. The tension force, not the force we are applying. As the body moves, the tension force is changing. You can see like this. First it was like this. Then as we go near to the pulley, the more it will become vertical. So in this type of question, what we have to do is we can't apply the direct formula F dot S, because here the force is not constant in direction. So we have to apply del dW is equals to F dot dr bar. F bar dot dr bar. So this is the small work. We have to find small work and integrate it, so we can add all the small works to get the total work we have done from bringing the body from angular position theta 1 to theta 2. So let's take an intermediate position. Let's say the position is theta and the angle is theta. Okay, so now here the body just moves somewhat forward. Okay, it just got somewhat forward like this, and here. Okay, so let's say this angle is d theta. This is d theta, a very small angle. So here is how this body moved, just a small distance. Let's say this is a distance x. X is the distance from this point A, which is vertically down of the pulley, to the instant point where the block is, and the block has moved some dx distance over here, and the angular position has changed with d theta. So now what we can do is, for small, this is a small change, so just we will write dw. So for now we will just write dw, then we will integrate the whole part. So what we can write the dw, since in these two cases the force is almost similar, it's almost, we can say that the force is constant, because we are assuming the d theta angle to be very small, so there is no change in the force vector. So we can apply the same concept of force into the displacement component along force. Okay, so we have to do a bit of mathematics over here. We also know that the vertical height over here is y and which is fixed. So now here you can take this triangle over out here. I am drawing it separately so it would be more visible. This is theta, since this is 90 degrees, and we have defined this as x and we know that this is y. So now from here, so we should also consider this small triangle. Let me highlight it. I will highlight it with blue color. See, this small triangle is very important here. So bring this small triangle out, because this small triangle is useful because since this is a small change of angle and we need displacement component along f, and displacement is in this direction, it's in this direction. So now we have drew this triangle. We know that this length in this triangle is dx. So if we somehow find out this length, so we can put it over here and then we can integrate on both sides to get the final value. So this is what we are going to plan. Since we know that this is a very small angle change, you can see that here, if this is theta, this is 90 degrees, this is 90 minus theta, and this triangle is, it's this triangle. I hope you are able to see it. This big blue triangle, right angle triangle, is this triangle which I have drawn over here. Okay, so now since this is 90 degrees, when there is a small angle change over here, then these two angles are almost equal. So we can say that these two angles are almost equal here. Let me highlight with another color. These two angles are nearly same. So we know that this angle is 90 minus theta. So we can write this angle also as 90 minus theta. So since this is dx and this is 90 degrees, we can write this as dx into cos of 90 minus theta. This is length of this side. So this is nothing but the displacement component of along, it's just the displacement component along force. So we can directly write over here that dw is equals to the force F into the displacement component along F. So it's nothing but dx into cos of 90 minus theta. Since we know that cos of 90 minus theta is sin theta, then dw can be written as F into dx into sin theta. So now here we have two types of variables over here. One is theta and another is x. So while integrating, we need to change this dx term into terms of d theta so that we can integrate it. So now take this triangle, this big triangle that I have drawn over here. Write tan theta by the basic principle. What does it say? It will say just x by y. So we can write x equal to y into tan theta. So differentiate on both sides. So we will get dx equal to, here y is constant. That's the important point. So here what the y is constant. So while differentiating, we will just treat it like a constant, not a variable, and we will keep it aside. So by differentiating tan theta, we will get secant square theta into d theta. So what we will get over here is So more important point over here is the dx is decreasing. As you see, this is x is decreasing. So dx since the x is decreasing, we have to mention the negative sign in the dw. Okay, so till here we have progressed in our dw. So now to eliminate our x, we have written this equation. So this equation is in d theta, so we can put it directly in dw. So what is our final equation? We will write in the next page. It's dw is equals to minus f dx sin theta. So we are putting dx is equals to y secant square theta d theta in the next page. Okay, so dw was equals to minus f into dx into sin theta, and what we found was dx equal to y into secant square theta into d theta. So now dw is equals to minus f into y secant square theta into d theta. Since f and y are constant, minus f into y secant square theta into d theta. That's all. So now final equation is dw is equals to minus f into y into secant square theta into d theta. So this is the small work done for changing the angle d theta. So we want it all over. So the small works totally adding from theta 1 to theta 2 will give you the total answer of dw. So we have to integrate it. Delta w is equals to minus f into y. So what is integration of secant? Oh, sorry, I missed here sin theta. So f into dx into sin theta was there. So there is a sin theta over here. Don't miss this sin theta. Let me erase this part. Okay, so it's secant square theta into sin theta into d theta. So we can write from here delta w is equals to minus f into y, and here we can write secant square theta into sin theta. One secant theta normally, another secant theta is 1 by cos theta. So sin theta by cos theta is tan theta. So integration of tan theta into secant theta, we can write this also. Okay, so from theta 1 to theta 2. So now we know that the integral of tan theta into secant theta d theta is nothing but sec theta. So integral over theta 2 to theta 1. So the delta w, the final work, we minus f into y secant theta 2 minus secant theta 1, which is nothing but f into y into secant theta 1 minus secant theta 2. This is the work done. So actually this is a very long procedure, but don't need to waste so much time in our exams. This is to make you understand the process, but for while doing in exam there's also another simple technique. So we will what's the simple trick over here? So here a simple trick is, so we know that here the work done by tension will be the work done by the force F. So work acting at this point is also same at this point. So this point, when we are going to here, the body is coming here, this point will move somewhere here and the force will be F, and the angle would be this would be, let's say, theta 1, and this angle would be, let's say, theta 2. Okay, so here y would be a constant parameter. So delta work done by tension is equals to delta work done by force. We can see it clearly. So the work done by the force, here we can directly write as force F into this change in length. This I am writing as delta L. Since the force and length, the change in length is nothing but the displacement for that point is in the same direction as that of force. So we can directly write F into S into cos 0. Cos 0 is nothing but 1 over here. So this is equal to F into what's delta L. So to find delta L is very easy thing here, because now we have like this. We have two triangles over here like this. If you draw it clearly, so the length which it moved is the difference between let's say let's say this is L1 and this is L2 length. So of course L1 minus L2 should be delta L. The change in length in the portion of string which is between the block and pulley will be the displacement of that point delta L. So we can write L1 from this triangle. So let's take the bigger triangle. This is L1, this is the angle theta 1, so this is 90 degrees and this is Y. So we can write cos theta 1 is equals to Y by L1. That means L1 is equals to Y into secant theta 1. Similarly, L2 is equals to Y into secant theta 2. So now here we can write F into delta L. Delta L is nothing but L1 minus L2. So it's Y secant theta 1 minus Y secant theta 2. See, you got the same results by a different process, but this was a simple one we have to use in exam. First procedure will clear your all concepts over this particular work thing, nearly all. So let's go to the next question. So what we should do when what is the work when force is a variable quantity? So let's say force is a function of position, okay, or force is a function of time. Then how to find the work? So what we have to do is directly delta W, as we know, integration of F dot dr. We have here it's changing somewhat, F in x direction into dx plus Fy dy plus Fz dz. So we have to integrate this whole thing. So this is when the the force varies with position, and when the force varies with time. This is for force varies with position. Now for force which varies with time, we have delta W is integration of F dot dr bar. So next what we have to do is multiply and divide with dt. So dr bar by dt into dt. Since we know that dr by dt is nothing but velocity, it is equal to F bar dot v bar dot here dt. So we know that we have not discussed it yet. Power is F bar dot v bar in general. It will come in our next upcoming videos. So we can write like this. Okay, the work when force is varying linearly with position. So suppose, now let's say that F is equals to K into X. Here x is the position of body in a, let's say, a straight line motion. Then what we can write, dw is equals to f into dx, which we are integrating on both sides to get the total work. So integral of f into dx is nothing but, let's say from the body is going from x1 to x2, put the value of f kx into dx. Here why I am not writing the dot product or all those things is because I am assuming that the displacement and force are in the same direction. It's a straight line motion. Okay, so what we will come here to know is kx square by 2, where it's going on x1 to x2, it will be half k into x2 square minus x1 square. This will be the final value. Okay, but here there is a very interesting thing hidden. Delta w we can write half k into x1 plus x2 into x2 minus x1. We can write this as half kx1 plus kx2 into x2 minus x1. So this would be half into f1 plus f2 into x2 minus x1. So what is f1? What is f1 is nothing but kx1, the initial force, and kx2 is final force. So we can write f1 plus f2 by 2 into x2 minus x1. So why this becomes interesting is because the x2 minus x1 is the displacement, and f1 plus f2 by 2 is nothing but the average force. So whenever the force is varying with linear position, whenever the force is varying linearly with position, then we can write the work done by that force is nothing but the average force. The magnitude of work would be the average force into the displacement, that's all, the net displacement. Okay, we know that the average force can be also written as integral of f into dx by integral of dx. This is nothing but force averaged over displacement. So we can write average force into integral of dx is equals to integral of f into dx. So this is nothing but the work done, integral of f into dx, and dx is delta dx, which is the net displacement. Okay, so this is always applicable. So this statement of delta w is always applicable, but there is only one restriction. We have to always check whether the force is averaged over displacement or not. That's the main question. If yes, then you can always use this. This is always correct in any time. Okay, so let's move to the next example. If a heavy rope of mass m and length l is lifted against the force of gravity, then find the work done in lifting the rope completely. So now here heavy rope, this is not a string, it's a rope. Let's say we have a pulley over here and there is a long and heavy rope over here of some length L and mass M. So what will happen here is we are lifting the rope on a horizontal surface. Let's say we are putting some force F, and at a particular point the rope is something like this. Okay, it's like this, and some y part of length is still hanging while we are uh, pulling it with a constant force F. Okay, so now for length L, the mass is m. So for y, of course it will be m by L into y, because actually it should be mentioned in the question, the heavy rope is uniform in mass. Okay, so mass is uniformly distributed over the rope. So for y length you will get this mass. There is also another condition in this question, that the rope is lifted slowly. Rope is lifted slowly. It is important because when they are saying that the rope is lifted slowly, then we can assume that at every point there is equilibrium. Okay, I hope you understand. So here we are, and one more thing, we are not applying any constant force, we are applying the force according to the mass which is hanging. Since it is in equilibrium, we know that it's mg, so for this point to be equilibrium, this F should be mg initially, and after that this should be m by L into y into g. I hope you understand, because the rope should be in equilibrium. The hanging part will exert a force of its mass m by L into y into g. Okay, so to balance that force, to go it slowly, we have to assume that at every point there is equilibrium. So F is this. I hope you understood. And when it is totally up, we have to do no more work. F is equals to 0. Here you can see that F is equals to m by L into y into g. So here F is directly proportional to y. So we are again uh, using the application of what we have discussed earlier. The force is directly proportional to y, and it is varying linearly with y. So we can directly write the work done is equals to average. So what was the initial force? Initially, when the whole rope was not lifted up, it was mg, plus at last when the whole rope was lifted up was 0 by 2 into the net displacement. For this case, we clearly know that delta W is equals to nothing but the average force into the net displacement. So if we see at any point, let's say this starting point, I am highlighting it with another color. This starting point is going over here finally. It's nothing but it's traveling a L distance, L displacement. Similarly, this is coming to here. So the displacement is nothing but L, clearly as we know. So the delta W would be nothing but mgl by 2. You can also solve this question in also in another manner, that dw is equals to f dot dy, means at this particular instant we are talking about this. So let's say the rope has come somewhat dy more, means the hanging part has decreased by dy, so the displacement would be dy here, and f into dy's integral would be the net work we need. So what would be the force? M by L y into g dy, which would be finally m by L into g y dy, and since y is going from 0 to L, we can write mg by L into L square by 2, which is mgl by 2. By these both methods you will get the same answer. If you are not getting the same answer, you should check your procedure. Okay, So now let's go to another example over here. Now you can see that our example is somewhat more complicated. Here they are saying that F is equals to xi cap plus yj cap. So the force is varying with position, and the force in x direction is changing according to the x coordinate of the body. So similarly in y, we for this case we know that we have to do delta w is equals to integral of fx dx plus fy dy plus fz dz. Here fx is the component of force in x direction, nothing more than that. You can also integrate in parts like this, you can, of course you know that. So assuming that initially the body it is at 0, 0 at the origin. So find the work done when it moves along x-axis to x equal to 0 to x equal to a. So for the first question, now we have this axis. I am drawing it over here, sorry. So this is our x-axis, this is our y-axis. Now this is something 0, 0. So from y-axis we are going to a, 0. So our path is this. This is our path. So now we can write that here x-axis is nothing but y is equals to 0. Okay. So what we can write here, delta w is equals to integral of x into dx. So there is no fz, so I am directly eliminating it into 0 because there is no k cap mentioned over here, into integral of y into dy. Important point over here is y is constant, y is 0. For this particular question number 1, the y is 0 because we are moving from x-axis and always the y is 0. So this would be directly 0 since y is 0 at any point. So y is not a variable in the first case. So that would be direct integral of x into dx, which is x square by 2, and from a 0 to a, so it would be nothing but a square by 2. Okay, so now in the second case, now let's go to the second one. Find the work done when it moves along the line y equal to a. So now we will draw our axis again. This is the x-axis, this is the y-axis. Now you are moving along the line y equal to a. So here this is the line y equal to a. Let's say this is at the distance a. So you're eventually moving in a straight line from 0, a to a, a. I hope you understand. So this is our trajectory over here. So what would be delta w would be again fx dx plus fy dy. No worries of the z part. So it's x into dx because the fx is the component of x and which is mentioned over here clearly as x, plus y into dy. So again here this factor will be gone to 0. Y is a, but y is a constant factor. In this particular trajectory, in this particular line, the y is constant. Y has a finite non-zero value. But since the value is not changing, we can directly write the dy equal to 0. Since it is y into dy of integral and dy is 0, so this whole part is 0. And again, it's the same, x square by 2, 0 to a, it would be a square by 2. I hope you understand. And now we will move to this next Next question. So this question is somewhat more complexer than other one, but this is not complex. I will tell you why. So it is F equal to x into y I cap. So the component of force along x direction also depends on the x coordinate and y coordinate. Okay, so now let's take the first case. Find the work done when the body moves along x-axis from x equal to 0 to a. Now just draw the same graph in the same manner what we had drew earlier. So this is the x-axis, this is the y-axis. Along x-axis 0 comma 0 to a comma 0, and our trajectory would be this. So we will write the fx dx integral plus fy dy integral. So there is no fz, so I am not writing it. This would be equal to what is fx is xy into dx. Xy is the x component of force plus y square into dy. Now here of course we know that x-axis moving along x-axis nothing but moving along the line y equal to 0. The coordinate of y is always equal to 0, and it is also not changing. So in this case dy is also 0. So we can directly eliminate this particular term, and we can also eliminate this term because y is constant and 0. Whatever maybe we do with the x dx, it's multiplying with y, which is 0. So this case is simply 0. Okay, so now let's go to the second case. So in second case it's saying find the work done when it moves from O to A to B, and the coordinates are given. I will also mention that it's moving in straight line. Okay, so it will make more sense. So again draw the coordinate axis like this. It's the y-axis, this is the x-axis. Now here we have to draw the points. Here it's the O, 0 to 0, 0 comma 0, A comma 0, and B, A comma A. So this is our path, first O to A, then A to B. So what we can do is the work done in this process, in this second process, would be work done going from straight line O to A plus work done going in straight line A to B. Since we already found the work going from O to A, which is the first case, this one is 0, so we can just cancel this term out. So delta W in second case would be integral of fx dx plus fy dy. So I am directly writing xy dx plus y square dy. So here in the process A to B, what is important is the x equal to A is constant. That means dx is 0. Means the x coordinate is not changing, so we can make this term as 0. And now only the y is remaining. It's y cube by 3 by integration. It's y is going from 0 to a. We can write a cube by 3. So the work done in second procedure is a cube by 3 over here. So now in the third question we have to find the work along the straight line path OB. So what we are going to do is draw a straight line over here, this one. Let me mark with the red one. So in this path we have to find the work. Okay, So we will do it in the next page. So f equal to xy I cap plus y square into j cap. Now draw the coordinate axis. Now we are direct going from O 0, 0. This is the third case. We are drawing O to B, B which is A, A. So what we can do is we know that y equal to mx is nothing but the line equation passing through origin. So we can directly write y equal to x because this line is passing through a, and as well as 0, 0. So here y equal to x in the whole path they are following in straight line. I think you understood. So now the delta w would be equal to integral of xy dx plus y square dy, which is nothing but fx dx plus fy dy. Now this is equal to, since x equal to y, convert all y into x, that would be equal to x square into dx plus x square into dx. So this would be nothing but 2 times of integral of x square into dx, which is equal to 2 into x cube by 3, which is going from 0 to a. So it's nothing but 2a cube by 3. Okay. So now let's go to the fourth question. In the fourth question, he asked find work done along path y equal to x square by a. So now we are going from O to A, but not in a straight line manner. We are going in a parabolic manner. So this is the graph. O 0, 0 and B is A, A. We are going this in a parabolic manner. So now when we are going in a parabolic manner, we can't apply this y equal x equal to y, all these properties we have applied in the third case. So our parabola is y equal to x square by a. So now what we can do is xy dx integral plus y square dy would be the work done, which is nothing but integral of fx dx plus integral of fy dy. So now just put y as x square by a, so you will get x cube by a into dx integral plus integral of y square dy. So that would be x power 4 by 4a plus y cube by 3, and x is going from 0 to a and y is also going from 0 to a. So that would be 4a, here a power 4 plus a cube by 3, that would be a cube taken common 1 by 4 plus 1 by 3, which is 7a cube by 12. So this is the final answer. And thanks for watching this video. If you found this video helpful, please share with your friends and like this video. Please subscribe to my channel, and I will meet you in the next video of this same series. We have not yet completed this chapter. So to complete this chapter, I am coming again with another new video. Until then, stay tuned.